Alright, the exam I've been prepping for. I was about to say for absolutely ages, then realised instantly that that's a lie. Sorry, I apologise for the background noise, I realised I did not have my power plugged in. But yeah, this exam I've not really been prepping for that long. Prepping for the past couple of days, and was prepping for some time before then. But probably have, well, actually, suffice it to say, I have only been efficiently prepping for this for, like, the past few days. That would be a more accurate thing. Okay, here we are again. But yes, that is soon. That is soon, and the number of videos which I've made whilst procrastinating for that exam will be seeing you guys through to this one will go out on the 6th of May. It's the 26th as I record this. So yeah, that should give you some idea. Why am I on this account? I was like, yes, this is the account I want to be on. No, it is not the account I want to be on. I literally looked at it and was like, oh good, it's already, this account's already selected. That's very strange, given that the last thing I did on this account wasn't that of an infestation, but you know, that's interesting. Well, the last thing I did here wasn't that interesting. It didn't make any sense, regardless. My thought process there. So let's actually go on to the correct account for what I'm planning on doing, which is Bat Infestation. I'm not going to do any more trying to work out what's going on with the ground pound bugs, because I think I made some good progress there earlier today, and I am in a mood for a vibe. And hence, I'm just going to do a Battle of Infestation run or two. It seems like it's the most fun thing at the moment that I could get done. So yeah, I have no idea what day-to-day life will actually do to my rate of video production. Realistically, exams shouldn't have sped up, or shouldn't have increased the number of these that I've done, but I think they might actually have done. Just because, like, come on. This is the perfect time where I'm doing, like, a good amount of work in a day. I don't have anything else to do aside from that work. So at the point when I, like, want to say, okay, I'm going to be done with this work for a bit. Like, I don't really, I don't know, my day is has less going on in it, I guess. Alright. So, let's go. Hoping for the best, expecting the worst, which, interestingly, is exactly my attitudes to tomorrow's exam. While my aim is off, because I'm kicking off the wrong side of my body. You know what, let's just quickly try and do this. Not quite. But hey, the good news is you're not gonna have any more of that stupid me being very sarky from the last time I did one of these about why haven't you guys reminded me to pick up any items, because at the end of the last one I did go and pick up some items, so you get no more me sarcastically accusing you guys of having messed up my runs, which is good. At least so I feel. A lot of confused stronglings right about now. Absolutely no idea which of them I can get off that and which I can't. Ba-da-dum, ba-da-dum, Ba-dee-da. Well, I'm bad. Let's just do that. Let's not die. Here. We doink. 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 Got a message from a friend today which I found hilarious. Being like, they were having, my friend and another friend were having a discussion about what the typical physicist looks like. I got brought up by my friend as part of this discussion, and their friend, someone who, I mean, I may have met. They did not name them, and I don't think I know. I don't think I know them. Just knew me based off of the description given of someone who always wore shorts and physics t-shirts, which is slightly apocryphal. Don't always wear shorts. Do always wear physics t-shirts, or at least a very, very large proportion of the time. So, yeah, on my behalf, make sure to give your local physics t-shirt wearer a wave next time you see him. Or just in general, I feel people wearing cool t-shirts, they'd love it if you came up and said, hi. I don't know, I've made it a point now, since I started recognising that this is an integral part of my personality, I started also making certain to go up and whenever I saw someone wearing a cool t-shirt to say, hey, nice shirt. Because, you know, physicists aren't the most socially adept of people. And I need all the help I can get. But also, like, I don't know, random compliments are nice. Saw someone at climbing the other day wearing a shirt, which was brilliant. It was just... I didn't actually read all of it, but I read enough to get the premise of it, which was... And the reason why I didn't read all of it was because I'm not good enough at climbing. The shirt said something along the lines of, if you're reading this, then you're doing the wall wrong or something. But the entire point was that the shirt itself was entirely, or the text was written entirely upside down. I was in fact not doing any climbs that required me to go upside down. Surprise, surprise. Therefore, I was unable. But I guess that may be surprising to you guys. You have no idea how good I am at climbing, or not. The answer is far closer to the not than to anything else. But yes, it was a funny shirt, and I made sure I gave it a compliment because it deserves it. Good shirt. 10 out of 10. Would enjoy seeing that shirt whilst climbing again. Oh, that was close. That was really close. Yeah, I'm not actually playing this incredibly well, but oh well. We'll survive. That is all that matters in this. That was close to me not surviving, though. That's bad. I really should go back. I really should work out on going back. Oh, do a little bit of work on going back to the normal strats for this. For the spiderlings. Because I feel like relearning stuff to take them down in fewer hits. I mean, the AI is slightly different on this server from what I'm used to. Thank you, very cool. The AI on this server is slightly different from what I'm used to. But, yeah, I don't know. I don't know whether or not it's... oh, I completely forgot which round it was. I had it in my head this was Merkel Bloch. Like how I've still not... Okay, there we are. First bit of damage I took that round, despite running through literally everything and not playing it safe at all. I'm literally just gonna see how long I can keep this up for. Oh no, kill. Oh, that was bad. That was terrible. Ah well. Such is the eternal grind of Battle of Nimbus Station. Was that said in an overly dramatic voice? Perhaps it was. I don't really care. I am. That's not overly dramatic for the sake of content or videos or whatever. That's overly dramatic because I am incredibly sarcastic for most of the time, and sometimes being extra dramatic helps give the sarcasm that little bit of flavour, you know. We all like a little bit of flavour to our sarcasm. We can't just have bland sarcasm. So yeah, I enjoy adding a little bit of nice seasoning. I don't know if I've mentioned some of my friends calling me out on sounding very Tom Scott-esque before. I don't know if I mentioned that on here. The fact that when I get particularly enthused about describing a topic, I don't really copy his accent, but because I think his accent is slightly different to mine. I think it might be slightly further north or something, but I get very, very close to his intonation. Which I will happily take. That is not the worst, the worst intonation I could copy ever. But it's interesting. I was explaining a question, or not explaining, definitely not explaining. I was talking through a question. I was explaining my idea for a particular question with a friend. A way of just seeing if we could get this done a little bit faster, because it was an absolutely horrific question. Yeah, I just heard from across the room my other friend comment on, oh yes, he's gone full Tom Scott again. Which I don't remember this, but it's a funny meme, so I will try and give it a go. For anyone who is partial to a little bit of computer file, well, that may already be a hint as to what I'm going to go for. I unfortunately cannot do it from the beginning. But this is Tom Scott attempting to. Well, this is me attempting to do Tom Scott, but not by attempting to actually do his voice. This is just by attempting to get really, really enthused about the same topic he's talking about, and then it just kind of. I've been informed, and once I've heard it, I can't unhear it. It sounds like Tom Scott. So this is him. This is him partway through a monologue about time zones, and then you get a call from Great Britain, and they say that. Oh, by the way, could you just add this into your code? We've just gone back. We've just gone back an hour because it's British, or forward an hour, I don't know, because it's British summertime. And you sit there and you're confused because you've already added this to the code, and you sit there for a little while. You ask them. You say, wait, but no, we've already done it, and they're like, oh no, sorry, you did summertime for the EU, but in Britain we go back and we do summertime a little bit earlier, and you're like, okay, you can factor it in. It's an edge case, but you know you can work with that. You can add that into the code, and so you do that. You sit down. You add that into the code, and everything seems to be all right. And then you get a call from your historian friend. And at this point, you're wondering why you have so many friends doing so many different subjects and living in so many places of the world. And your historian friend turns to you and says, "Oh, by the way, your program gets it wrong with these dates." And you're like, okay. What's going wrong? What's going on with this? And like, well, you see, this was at the point in time when people decided, when Pope Gregory the Third, I think it might be, transitioned to the Gregorian calendar. And yeah, there was a period of about a few weeks there, which never happened. So if you could just write that into your program, that would be brilliant as well. And then you get a call. And then you get a call from someone. I don't know. I don't remember any of the countries in this. And then you get a call from someone living in this particular country, and they say that I think Libya at one point had this. I think this may have been Libya. And then you get a call from someone in Libya, and they say that actually we've just changed what time zone we're in. So from this date onwards, you need to account for the fact that all the times will be given by this time, and by this point you're really starting to get tired of this all, because what started off as a small project to write a program that could tell the difference in time between two different dates has become so much more than that. You have added in so many edge cases, so many exceptions. You attempted to fit it into a structure and to have nice style, but past a certain point everything is being changed by everyone around the world, and you have absolutely no hope of fulfilling every single edge case. There's stuff like the Unix timestamp, which tries to make better sense of this. The Unix timestamp basically being the number of milliseconds which has elapsed past a certain time, and so you implement that, but then you get a call from your astrophysicist friend, at which point, as someone who likes their physics very terrestrial, I would ask why you have an astrophysicist friend. But you get a call from their astrophysicist friend, and they say, oh, by the way, it's 2020, we're coming up for a leap second. And at this point you put your head in your hands and you begin to cry, because you ask them what a leap second is, and they explain that, well, the Earth's rotation around the moon, it's like, you know how you have leap years to account for the fact that, well, days don't line up precisely with a year, and we have slightly more than 365 days in a year? Yeah, well, it turns out we also messed up and the seconds don't work precisely either. And so you write this in, but you look at your code, you look at what you have produced, and you see a complete and utter buggy mess. It is awful. You look at what you have created, and you realise that there are still more people on your phone, there are still more people who want to use your library for different use cases, and you realise you have made a mistake. And so what you do is you throw away all your code. You throw away the spaghetti code that you've added on one edge case at a time. You throw away that humongous switch statement which has made the entirety of your code work. You throw all of that away. You then go online. You go to Google, and you go and you look up the problem, and you find the open source libraries that have been written by people in the past, by the people who have tirelessly worked to add all of these possible edge cases into their code, and to keep them up to date. You look up, they've kept up to date with all the tables of all the time zones, and they've managed everything. And you look to them, you say a huge thank you to them for making their work open source, and you never ever look at time zone code ever again. I imagine that would have sounded even more Tom Scotty had I actually known what I was talking about through half of that, and so half the facts in there weren't made up. It's very much like my the nonsense I did the other day about Battle of Nimber Station. I'm far better at talking quickly when I'm making up utter nonsense than I am when I'm saying something that's actually the truth. It's a lot easier to talk quickly and enthusiastically about that unless you've had a long time to think it out in advance. There are certain topics I probably can ad-lib like that. Well, there are certain topics I know I can ad-lib like that on. One of them being wave-particle duality. But I've already published at least one video on that topic. I've published, I think, one video on the Ninja Warlock channel on this topic, and another one on another channel that will. Which I did with some friends a while back. But yeah, I do find it interesting. It's weird the sorts of things that I can and cannot do that kind of ad-libbing with. I do, yeah. One of the ones the wave particle duality rant is a very, very fun one, and this was where I think this might have been the first place I got outed as being Tom Scott-like, because by my friends, because I can hear the resemblance between that and his and then's. from the time zone thing, because it's basically, the more you go, the more you realise that waves and particles are not really well defined, and there are a ton of and thens as you realise that, wait a second, this thing you thought was a particle, although this thing that you thought was a wave, well, it turns out that when you have the nonlinear corrections, that too becomes a particle. And if I did all rant, it's good fun. It's good fun. But basically the point was, I was discussing. Run. I was discussing about quantization and quantum mechanics, and about waves, particles, and mass, which are all interesting topics, but all surprisingly difficult topics. So in particular, the question of you can fairly easily, I say fairly easily, that is not true. You can, if you spend enough hours on it, you can work out. You can do some algebra. You can write what's known as Lagrangian, which describes the equation of motion, or it's the most general equation of motion you can come up with, which is to like second order. So it has some certain like nice locality properties, more or less. So it's kind of like a nice, well-behaved function, and you can sit down and you can do some work on this function. Yeah, this is the simplest function of a certain kind, and the reason why I've come up with this function, this simplest function of a certain kind, which basically obeys a set of symmetry properties, is that it's a particular way of looking at physics, which is that a good way of coming up with theories that describe particular things in the world is to look at the symmetry properties that those things obey, and to come up with basically there's a quantity in physics known as the Lagrangian, and you can use it to work out basically the equation of motion of a system. It's a really helpful tool to have in your toolkit, because you have one number which includes the degrees of freedom of the system, or one function which includes the degrees of freedom of the system, and it gives you the dynamics of the system. It's really, really helpful. And basically the idea of a lot of stuff, I mean, including many modern derivations of the standard model of particle physics, is basically like, okay, let's try and look at the simplest thing we can have, which obeys the particular symmetries of our universe. So in particular symmetries, we'd typically like our universe to have, at least if we're ignoring quantum gravity, the symmetries we'd like our universe to have are a particular symmetry group called SU2. Okay, no, there might be more, but I'm not a particle physicist, so I'm going to say SU2 here. And basically, these correspond to space-time symmetries. These correspond to special relativity. With general relativity, it gets more complicated. You have to deal with diffeomorphisms and things which I don't understand. Basically, the idea that the laws of physics, or you should be able to express the laws of physics in a way which are coordinate independent. And that's the notion of a diffeomorphism, and that's arguably the fundamental thing underlying general relativity, and certainly a lot of the maths we do to make general relativity work. Okay, this has been one of the more cursed things I've done. Why do those two run at exactly the same speed? It's annoying. Wow, I messed up my chance to get rid of them. Okay, that's better. That's better. Okay, we're good. That was scuffed, but I kind of enjoyed it. I could have made it less scuffed, but you know what? It's more fun this way. I'm gonna head out. Do not want to be dealing with you. Okay, I am gonna de-aggro the Spiderling to deal with the Hammerstromlings. Hammerstromlings are more effort than I want to put in. Of course, there's another one of you. Okay, let's do this. But yeah, so basically what you can do, you can take some symmetries of the universe and you can write down something that is literally a number. You know you have some degrees of freedom, and those degrees of freedom possess some symmetries. So for instance, a classic one is your degrees of freedom are your x, y, and z coordinates, and you know, for instance, that you have some rotations between them. That's not necessarily the symmetry group that we'd like to use in modern physics. There you'd actually want like space-time rotations, which is the SU2 group I mentioned earlier. Or which is related to that, if I recall correctly. I'm no particle physicist. But yeah, the interesting thing is this notion that, yeah, we've got this thing called the Lagrangian, and we can encode a number of degrees of freedom into that. And I'm dead. I didn't process that I'd been hit. Largely because I was talking too much. Who'd have thought? So basically, we plug our degrees of freedom, and we get this. And the idea is basically that, okay, let's try and do physics by let's like come up with the simplest thing we possibly can and see how well that models the real world. We can then add extra terms if that doesn't model the real world particularly well. But the idea is that if we know the symmetries the real world is obeying, then let's like begin our descriptions of the world by considering like the terms which would contribute the most strongly. Or which hypothetically would, terms obeying that symmetry, which do contribute strongly. If it turns out that they contribute like particularly strongly or particularly nicely, then brilliant. We've done very well. If it turns out that like strong contributions by those terms isn't actually a thing, then we might have to say, okay, experimentally these terms appear to be 0. Well, they appear to be small, and we can then maybe try and hazard a guess as to reasons why they might be small. But this is a good starting place for a lot of modern physics. And so basically what we can do is we can say, okay, let's take the symmetry group of the universe and let us come up with a scalar field. And in particular, we're going to come up with a complex scalar field. This is basically just saying, okay, we kind of know from quantum mechanics that we have like I guess the group would be U1 maybe. Maybe it's SU, I don't know. But we know that we know that complex numbers exist in our universe. And in some sense, you can rewrite the Schrodinger equation without them in theory. It's just ugly and not worth doing. We're going to just take the real and imaginary parts of the Schrodinger equation. I don't know if you can do... Yeah, I mean, you should be able to directly substitute them back into one another for a second-order differential equation, because they are just... those two would just be two coupled first-order differential equations at worst. But anyway, yes. So this is a way that a lot of modern physics is done, and what you get when you do this is you get what's known as the Kline-Gordon equation. And the Kline-Gordon equation is I don't actually know how useful it is. Off the top of my head, I don't know which particles it describes, if it actually describes any. I think it describes a single spinless particle. So a single spinless particle but with mass. So I mean, it doesn't describe a photon because they do have mass. Oh, sorry, they don't have mass rather, and this does. But anyway, you can come up with the, I mean, yeah, anyway, we'll get to mass in a little bit. But yeah, you can come up with the Kline-Gordon equation. It would basically, mass kind of arises naturally in the Kline-Gordon equation if you add like an extra perturbing thing. And then you get, yeah. And it turns out you can also add that extra perturbing thing by adding an extra field that it interacts with, and that's the Higgs field, and the Higgs field has mass, and that's how we expose something. But yeah, so basically, more or less the idea is that you come up with like the simplest particular model that a spin zero particle could have. Wait, what am I talking about? Photons have spin! Of course it doesn't model a photon. Idiot. But yes, so I actually have no idea what this would model off the top of my head. I guess there are lots of things. There are like, I mean, there are lots of like simple quasi-particles which don't possess spin, which you could say for this. So I guess that would be the answer. But anyway, it turns out, and like a nice way of thinking about it for me is you can make a direct correspondence between this and between a if you imagine you take a skipping rope and a rod. Do I want a skipping rope? I forget exactly what I want for this. Yeah, I mean, it's close enough. I'll take a skipping rope and a rod, and I have the skipping rope under some tension. And we know that if I just tie the ends of the skipping rope to the rod, and I move it up and down, that we're going to get waves on the string. And I don't need to tie them to the end of the rod for that. I can just hold it between two friends, and we can move it up and down, and we're going to get waves traveling along the string. Congratulations! This turns out is it turns out that the complex numbers in the Kline-Gordon equation actually map really well to just being x and y components of your wave. So if your axis is lying, so if you imagine your string, your rope is at rest and perfectly flat, and you let the axis along which the rope lies be the z-axis, then your real and imaginary parts correspond to your complex scalar field correspond to the x and y axes. So basically, this entire field can be represented by just having a string, or at least to begin with, we can start understanding this by a string. The issue is there's actually an extra term. Well, this is for zero mass. So zero mass, you basically just have a rope, and that is your Kline-Gordon equation for a field for a particle with zero mass. If you decide to add mass to it, then what you get, and this is the neatest way I can come up with for visualizing the field. I'm bad. Oh, I'm not. I dodged that. I'm good. Didn't dodge that. I didn't even try to dodge that. Why didn't I try and dodge that? But yes, if you choose to add mass to this, what this corresponds is to taking the rod. So this rod was the z-axis. It's the axis along which the rope lies when it rests. You then basically add a ton of springs to that rod. And these springs attach every point on the rod to a commensurate point on the rope. And so the idea now is that, okay, that basically the rope can be perfectly flat, and if you pull the rope away, if you imagine the rope was rigid, or you were able to pull it away such that it was perfectly flat as you pulled it away, then it would, it would bounce into the rod. But if you imagine the rod is there for the purposes of keeping the rope in place, but the rope can pass through it, then basically you can have the rope be perfectly flat and just moving up and down. And that's exactly the same way if you just got a mass on a spring and you just pull that down, that will oscillate up and down. This is just, I've put a lot of masses in a row on some springs and I've joined them up. And so it turns out this is actually a fairly good way of understanding the Kline-Gordon equation. It's not perfect, but it's not terrible. It's not perfect specifically because it obeys the same equation of motion in one frame, but it does not have the property that it is relativistically invariant. Is invariant under the transformation of special, or Lorentz invariant under the transformation of special relativity. So yeah, moving on, whereas I've been blathering about that for far too long. Basically, the point is that, wait a second, this Kline-Gordon equation, I've just said that this has mass, and this mass is somehow related to the fact that the I don't even see that coming in advance. This mass is in some sense related to the fact that if the string is flat, it can still oscillate up and down. The reason why this is related to mass, you can think of as coming from E = mc squared. You don't have any waves traveling back and forth, so this has. Yeah, okay. So I guess what I should introduce first is the notion of a quasi-particle, and this is where the whole rant comes from. Because what we find is that it's actually sometimes really, really helpful to say, okay, an oscillating string, or a string oscillating in a particular way, is not a string oscillating in a particular way, but it is merely a particle existing in the space of configurations of the string. So basically, a particle, I can define fairly arbitrarily for now a particle as being just a particular way in which this string can move. It's literally just a way in which a string can move. Now, is that useful? Maybe, maybe not. It turns out it has some useful properties. It turns out these behave. It turns out these things are bosons, and they actually are fairly useful in life. But yeah, how but yeah, on its own, this might not be incredibly useful. You could do this all without the notion of particles. The particles let you use the algebra and language of quantum field theory, but what if you just... But you could solve this problem anyway without that language and formalism, so why bother? Well, the interesting thing comes in, or what I find is an interesting way, a nice way of thinking about it, is when you start getting nonlinearities in your problem. So nonlinearities occur when superposition isn't obeyed. So in other words, if I am just barely like moving a rope up and down, and I want to look at waves on that, when I do the maths to work out what shape the waves are, I'll typically find, well, I've said they're waves. That means they obey the wave equation. The wave equation, however, is a linear equation, and as it turns out, the motion of waves on a string, is not a linear equation. Why is that suddenly my... Okay, not one of my best times suddenly. Chain... Oh, no. Okay, ignore that. So yeah, there's a question. So we can basically say, okay, these waves on a string approximately obey this linear equation. What this means is that if I send a wave down there and someone else has sent a wave down there from the other end, those two waves are they're just going to travel straight through one another. They're not going to bounce off one another, which kind of makes sense. However, this doesn't really hold indefinitely. In particular, if you just consider the fact that, well, the length of the string is finite, and if you're saying it's fixed at both ends, okay, if you're making really, really small oscillations, then maybe the fact that the length of the string is finite doesn't make, or the length of the string is constant doesn't make too much of a difference, because, okay, they're small oscillations. The change in length you can show is, I think, second order or something like that. I think, I'm not actually convinced it is, but anyway. You can do some work and find out what the change in length of the string is. No, it should be second order, shouldn't it? I think. Doesn't matter. You do some maths, you work it out, and you find that, okay, you can neglect it. But the thing is, that's only for like really, really small waves on the string. The second you start making a large wave on the string, well, you can't really ignore this anymore. And like that's obvious in the fact that if someone does send a really, really powerful thing down the string, well, that's going to basically wrench the string out of you. Well, in order to make that wave, like, you need to... That wave has a certain height, and there is a certain length of string contained within that wave. Because there's a certain length of string contained within that wave, it must have pulled the other end. And now there's no way we can assume that, like, waves are independent, because we've literally got the like, apparent length of the string that we're doing maths over has, like, we've pulled some string away from the other end. This can't possibly be completely linear. These things can't possibly obey superposition. They have to interact with one another. And so there was a question as to how exactly they do interact with one another. And if you want to start doing this, a really nice way of doing it is to then say, okay, I'm going to associate these waves with particles, and I'm going to basically say that, okay, these particles have a certain momentum associated with them. It's often known as the crystal momentum, because typically it gets used in crystals. That's roughly the image I'm drawing from in my head right now. And in this case, the actual things are sound waves, and they're called phonons. Yeah, so we've got some waves moving through some crystals, and basically, if we've got some nonlinearity or some anharmonicity, whatever you want to call it, basically, the more complex or the larger your waves start to be, the more their size, or the more other waves matter. The easier it is for things to bounce off of one another. The easiest way to think of that, I guess, is if you imagine you have an incredibly strong sound wave, and it's like propagating through like a rod of a rod of steel or something. Incredibly strong sound wave. Well, what's going to happen? These are just vibrations in the atoms that are carrying the sound wave, but this is really strong. You've managed to get these atoms so they are, because the sound wave is so incredibly strong, these atoms are nearly touching, because adjacent atoms are moving significantly differently relative to one another as the sound wave passes through. It's an incredibly powerful sound wave you've managed to generate. That means you've got some regions which are incredibly dense and some regions which are really not. And what you end up finding is that if you send a short wave through, or as if you send a not shorter but a weaker wave through, then you're going to find that you basically get reflections off of these. That effectively your smaller wave, your second wave you're sending on top of the first one, is going to bounce off. And it turns out that when you actually want to analyse how these are bouncing off, a nice way of doing it is saying, okay, these are particles with a particular momentum, we can consider them in a certain set of waves, and when they interact with one another, we're going to be a little bit blasé with how we say they're interacting with one another. We don't really know. This is in the details of the equation. I mean, you can work it out, but like that would quite often just require simulations. If we want to do like calculations with this and get analytic answers out, we can't really handle this. So what we do is we just say, okay, all right, I'm just going to say these are particles, and we know that we're in a system where certain conservation laws are obeyed. So let's just say the particles obey those conservation laws. We can show rigorously that if we create some sets of particles in these systems, then they do obey the conservation laws, and like, GG. You're basically there. You've now said that, okay, we were dealing with waves on a string, but to deal with the fact that superposition isn't precisely obeyed, we can say that, okay, what was one particle is now actually multiple particle, or what it was now a wave is now, we're going to term a particle in such a way, in some way, and we can then understand phenomena by these particles reflecting off of one another, or bouncing off of one another. It makes it easier than considering waves. And this is the basis of, for instance, Feynman diagrams. But you may say, well, wait a second, Ninja, those things in the Feynman diagrams, aren't they particles? And the thing is, on a quantum mechanical level, the answer is, well, no, not really. They're described by a wave function. That's a wave. That's the bit which always weirds me out about particle physics. I spend a lot of time treating them as particles when realistically they are waves and waves/fields, and so like QFT is. I don't know. Every time I've ever been taught particle physics, it's been a lot of not QFT, and it's been like, oh, we're using like quantum mechanics. We're saying like this electron has a wavelength, and yet we never say what its wave function is. And we never ever consider it having a wave function. We always say it's a particle. We say it's colliding with something else like it's a particle, but we say it as a wave function, which is fundamentally not a property of a particle. It turns out there are ways you can make this more reasonable, but I still haven't done a particle physics course that actually teaches that. People who know me in real life may know that that's because I stopped taking particle physics courses because I was sick and tired of them not teaching me that before they ever did get a chance to teach me it. I don't care. I do not apologise for my actions. Yeah, so essentially, it comes to, you start off being like, okay, so this was kind of all the run up to the rant. So, we begin with fields. Or we begin with two bodies. And we say, okay, I want to know something about the forces between these two. And so we can begin by saying, okay, well, I've got a formula. Let's say Newton's gravitational law, F equals gm1 m2 over r squared, and this formula is going to describe the forces acting on particles anywhere in the universe. Okay, so we start off with this, but then what people do is they start trying to say, okay, wait a second, what's actually the potential energy here? And it's like, okay, we can start to work that out. So it's a little bit of scary stuff over the self-energy, but, you know, by considering certain arrangements of particles, we can avoid that. And people do that, and they find out, wait a second, that's weird. When we did that, we found that actually we can work out the potential energy solely as a function of the field being exerted by a set of objects. So actually, I can work out the energy entirely in terms of the gravitational field, and this is really interesting. I can always let's be careful. I can basically no, that would not be a correct statement to make. But yeah, so we begin by being like, okay, these fields are literally, I can just envisage gravity as being a series of arrows pointing in a series of directions throughout the universe, and that's really, really helpful if I want to, for instance, like get a rough idea of trajectories, because I can draw out a ton of arrows. Assuming gravity is smooth enough, I can then basically connect arrows end to end, and I can plot roughly the path I think a particle would take. It's slightly more complicated than that because you've got to take into account of inertia, but more or less that's a good start to handling particles, or to handling fields. But then you get this weird thing where actually when you consider this potential energy, it's like, wait a second. When I consider this potential energy, this seems like the field's carrying energy. Now bear in mind, this is solely a rearrangement of this equation I had that described particles. This is rearrangement. It does not say that the field is carrying the energy. But then you can think to yourself and think, but wait a second. If this equation doesn't mean that the field is carrying energy, did that previous equation mean that the particle was carrying the energy? The line gets a little bit blurrier. And then we can start thinking about stuff like light. Because light is far, far, far more easily understood as a field than as anything else. It's not uniquely able to be understood as a field. A kind of useful thing that was done in this area, not by Menke, but named after him, was Menke's equation. So the reason they were named after him, because he used it more or less to argue this exact point, which is the fact that fields, that we very, very often describe light as being a wave, but we don't need to. In fact, we can describe the force, we can describe the action of particles under a force fairly simply. And I can describe the force a particle feels from an electric and magnetic field fairly simply, and I can describe the forces due in the entire universe to my particular set of magnetic and electric fields. I can describe the magnetic and electric fields entirely due to the particles. And so wait a second, I can actually describe the entirety of forces in the universe without once invoking the notion of an electric or magnetic field. I can come up with notions of momenta, which are perfectly well conserved. They are ugly as heck, but they are perfectly well conserved. So the classical thing is, but we need a magnetic field to carry momentum, right? Because we know that when light hits something, it transfers some momentum to it. Stuff like that. And we know we need the electromagnetic field to carry momentum. And another reason we might argue that is if you just imagine locally a particle moving through a magnetic field. If you have locally a particle moving through a magnetic field, then what you find is that the magnetic field... Yeah, bad. I'm not playing that well. The Menke helped me out there, honestly. What you find is a particle in a magnetic field, a charged particle like an electron in a magnetic field, it perfectly well conserves energy, doesn't conserve momentum. Because charged particles in magnetic fields do orbits, make orbits, and that's actually one of the ways that originally the charge to mass ratio of an electron was discovered. It was discovered by considering the radii of these orbits. And so you might think, okay, well, we need a magnetic field in order to conserve momentum, but here's the thing, you actually subtly don't. There is an expression for the momentum of the particle, including the magnetic field, and it's a lot neater and arguably a lot more local if you do just directly include the momentum as being in the particle itself, but we already discussed that we can describe the magnetic field of something entirely via Menke's equations. If the magnetic field is in some formulaic way carrying the momentum, or is required in the momentum conservation equation, well, I can just substitute in Menke's equations. The momentum will then, it'll be ugly as mentioned, but I'll be able to substitute in the magnetic field, or in this case it'll be the magnetic vector potential, in terms of all the other particles in the universe. And I can just say this is some momentum attributed to them. I don't need the magnetic field for it. Magnetic field makes the maths a lot easier, and it makes it a lot easier to visualize that, hey, we've got this particular field that is we've got this particular field that's carrying momentum away, and hey, it's a little bit like a wave, and maybe that's how it's carrying momentum away. But it doesn't necessarily have to have that physical meaning. That is just an interpretation of the equations. It's a really neat one with light, but it is just an interpretation. So we have these things called fields, but the more we do, the more it seems that, like we're saying, fields are becoming more and more important, more and more interesting, and we have no reason to cling on to the particle-like nature of things. That's the main thing to note. The particle-like nature of things was really helpful in classical mechanics. But if it's not helpful anymore, there's no reason to stick to it. Equations don't come necessarily, or basically never in physics do equations come with a single, uniquely well-defined interpretation. Physics just doesn't do that. Instead, you've got some things which will determine the motions of some things. Maybe it won't even determine the motion of actual physical things. We don't know yet. And certainly with light, it seems like this isn't the easiest way of going about things. So what we can then do is we can see, oh, okay, let's maybe go about this differently. Let's see if we can actually try and derive the existence of light. And it turns out you can do this in a very similar way I discussed the Kline-Gordon equation earlier. You can basically say, okay, what is the simplest interaction we can have that obeys a particular symmetry group, in this case SU2, so the group of quaternions, for anyone interested. What is the simplest, field we can have which obeys this? And note we begin here with fields, because it's actually, particles don't really, it's fairly difficult to write a particle, an equation for a particle which obeys properties like this. And it turns out that we can retrieve all of the behavior of particles if we just consider fields. So why bother consider if it seems that that fields represent particles fairly nicely and arrive directly from symmetries of the universe, why bother with the particles to begin with? We do this and we derive optics, and this is a good start, and we're like, wait a second, let's see if we can go any further. And we sit down with a pen and paper, and we begin to derive maybe the Kline-Gordon equation. So we derive the existence of a particle. We note how with a perturbing field, we derive the existence of this thing which maybe will behave like a particle. But we can begin to derive the existence of these interesting fields that in some senses do seem to behave like particles. We haven't really defined how yet. But we note that if we do the maths, and I got very lucky there, we note that if we do the maths in a particular way, and we make some, if we try to consider, so we noted that for optics we could consider this field as being something that physically existed. Sorry, I guess so. I should point out that the reason we're doing all of this is we're getting closer to being fields as things that physically exist, because that's just the first point we want to think about. Do fields exist? And waves kind of naturally occur in lots of fields. I'm not trying to prove that waves exist necessarily. Can I not do? Okay. I'm doing an absolutely terrible job of this because, well, I'm trying to play this. I'm actually doing a terrible job of both things I'm trying to do at the moment because I'm trying to do the other at the same time. Doing an absolutely terrible job of battling the station. I'm doing an even worse job of explaining this physics. So perhaps I should just stop and should turn to a slightly different topic or a slightly lighter one. which requires less brain power from me, because as many of you watching who have watched for a little while will know, brain power is not necessarily my specialty, and certainly not something I can often conjure up on demand. But yeah, essentially the really interesting thing is that we begin with fields as this notion that they don't exist, and that they just act on particles, and they exist solely to make calculating the trajectories of particles easier. We then realise, wait a second, there are certain fields which maybe math is almost easier if we say they do exist, and so we start working with those, and then we say that, wait a second, but the maths gets even easier when we add nonlinearities to those fields. If we say that, well, those fields are actually... that the different ways those fields can oscillate, the different waves those fields can possibly have, well, they're just actually new particles. They are quasi-particle oscillations of the fields. And then we can start looking around at other places in the universe where we have particles, and we can see, wait a second. What? Maybe we can just write this particle elsewhere. Like, what about the electron? If we're saying that we can get quasi-particles out of some of these things, well, what says the electron couldn't be a quasi-particle? And people do the maths. Dirac did the maths. And it's like, wait a second, this actually... You get something that behaves like an electron if you do this. And additionally, on top of this, he did even more maths, and he found that, wait a second, not only do you get something that behaves like an electron, you even predict the existence of something that behaves like an electron with the opposite charge, which we'd later come to know as a positron. Although it was initially thought that this could just be the proton itself, which I find quite interesting, because it's often like, oh yes, and therefore he knew it was the positron. He didn't. The positron hadn't even really been theorised by that point, I don't think. And it was only later experimentation which confirmed it, and which ended up naming it, and which ended up calling it out as basically being the antiparticle. However, it does have some interesting properties, because you can get something that's like charge, and you can get something that's like an antiparticle, even in the Klein-Gordon spinless system, which I described earlier. And these I kind of enjoy, because they are awfully easily visualized. I cannot visualize Dirac spinners, whereas I can fairly easily easily visualize waves on a string. And it turns out that charge, when it comes to waves on a string, is literally just two waves on a string moving. It's literally just the string rotating in two different directions. Now, this is not in any way trivial, and I cannot precisely prove this. I can demonstrate certain things about, okay, if we move around our axes a little bit, we can get... if I basically choose to relabel my x and y coordinates along my string, with different rotations, depending how far along the string I am, then I can get something that looks like it's an additional force acting on this. Acting on those coordinates. So if I redefine my x and y coordinates and move along the string, and then plot the x and y coordinates on like a single graph later on, I can get something a force which looks as though it's acting on those coordinates. So I basically then... I redefine my x and y coordinates at every point. I do the experiments just as normal, but I then, when I'm looking at my results, I then twist my x and y coordinates around a little bit at every different point on the string, so I effectively twist up the video a little bit, and if I do that, it turns out that it looks like I've got a magnetic field acting on them. Now, this is often quoted as deriving the existence of a magnetic field, and I cannot stress strongly enough that this is not the case. It's not what it's doing. And why do we know this isn't what it's doing? Well, because we know there's a frame which we can transform to, which completely gets rid of all fields. I should say it's not just the magnetic field that's generated by this, it's both the electric and magnetic fields. Whereas, but also we can find that there is a frame we can transform to where we get rid of all of the fields. And that's not true in general. Electric fields, I can normally get rid of like the electric or the magnetic field instantaneously, but I cannot get rid of both of them. And so this isn't actually a good derivation of electromagnetism, but it does give us our first hint at it. which is that, yeah, depending on how we look at this system, we can appear to have a magnetic field. We can then say, okay, what is the next simplest thing we can add? What would a magnetic field... What would happen if this thing were more general? This thing that came out solely from our symmetries, what happens if we just added that, but a little more general? And then you do get a magnetic field, and then life's happy and life's good. And you can see that because, like, you can kind of intuitively understand that, well, this was actually just a warping caused by the fact that I chose to rotate, I chose to redefine my x and y coordinates, or my x and y directions, as I moved along my rope. If I, and so it was fundamentally related to my x and y coordinates, and so it turns out what charge is, and so, like, and it's fundamentally related to, the field is fundamentally related to how I change my x and y coordinates as I move along. And therefore it kind of makes sense, if my field is related to how I change those coordinates whilst moving, it should make sense that fields which are rotating in different directions with respect to my coordinates should behave oppositely under my field. And that's kind of what we get out. And so, yeah, you end up with some notion of the electric charge from this. Honestly, a lot of this I just need to consolidate myself. Because there's a lot of physics in these kind of areas which are deeply and intrinsically linked up and which I do not fully understand. So, for instance, the Berry phase is fairly commonly deeply related very closely to the magnetic vector potential, for instance. That's... honestly, I found it quite hard to make rigorous at certain times, but or to make intuitively rigorous, because I can explain away the Aharonov-Bohm effect in theory. Well, yeah, that's kind of gets cyclic actually. But yeah. But anyway, yeah, it turns out that in reality there tends to be, the more you go, the fewer and fewer distinctions you tend to have between particles and waves, and therefore the original question, which I was once asked, which led me to a particular rant, which I didn't really do today because I'm tired and I'm not thinking efficiently enough, was, what is the smallest thing? And the answer is that, well, it's really hard to define what size is to begin with, because size is inherently a somewhat particular, well, it's not even an inherently particular notion, it's just a weird notion, because it can't be inherently particular, because, or it can't usefully be inherently particular, because lots of things we're told about say that particles have zero size. Honestly, doing this like extra attack or two on the end, saving me a lot of these. I mean, not as many. It's not saving me as many as I've lost today through sheer incompetence, but it is saving me a number of them. It's making me a little bit more efficient with those, which tends to mean they get less out of control, which tends to mean I'm a happier ninja. You can also probably hear that after all the ranting I've been doing, my voice is slowly beginning to die. So let's sip of water quickly, and maybe I will stop talking, and maybe could actually make it to Merkle Blotch today if I, actually concentrated on the game. I do apologise to anyone who watches these videos, as always. Again, you never really get any good content out of these, because it's always like, it's not normally, it's normally random, broken up rambling, because I can't ever concentrate because I'm trying to play a game at once. I don't know if people who like stream professionally are just better multitaskers or whatever, or if they just don't try and get into as deep or as long topics, or if they do, they're helped kept on topic by the fact that people are replying in chat. I don't know. Don't know how they do it. It could well just be they are far better at this than I am, and that seems a very, very reasonable hypothesis. And you know what? That's a hypothesis I'm pretty happy with. Hey, doink. So yeah, please take your bets now as to whether or not I will actually manage to complete this safely. If you bet correctly, then I don't know. I mean, I'm not saying guess and I'll give you a reward. I'm saying, I don't know, take a bet with whoever's next to you and whoever's judging you for watching a stupid ninja video. Oh. Alright, that's... I would be very happy if we could actually make it to Merkle Blotch after the amount of blundering I've done, because let's just see. We are 1 hour and 5 minutes in, and I have not made it to Merkle Blotch once. This is not what progress looks like. So yeah, okay, 2 seems to be roughly safe there, normally. Oh, that was incredibly close. I don't like that at all. Okay, we have finally made it to Merkle Blotch after a lot more stupidity than we really should have had. Entirely me being an idiot by trying to bite off larger topics than I can chew, whilst also playing a game to any reasonable degree. But then again, those of you who have watched this for a while will not be surprised with any of that. So, let's go. Merkle Blotch. I'm going to resist my instincts and not heal up. I was about to say I'm also going to resist my instincts and only ever attack once in a row, but I then instantly failed that. So, you know. Instincts die hard, I guess. Times. Poor Merkle. No, maybe not poor Merkle. Maybe I take that back if I'm going to do something stupid like that. Don't be fun for him to be the one boss that I can literally just run around in. Actually, I don't know. I honestly think King of Her was probably easier. The funny thing with King of Hell is that I can't stun lock him. But despite that, like, it's not too bad because I can effectively stun lock him, but I don't even have to attack by simply being close enough that he won't use his ranged attack, which is, yeah, I'd say life hacks. I should also find out what pens are in my room, given I've got an exam tomorrow. I don't know what those are. So I randomly just mute this and get some use, and just whistle. Wait a second. I muted that for you guys, not for me. I'm in the mood for just randomly whistling. And now I feel incredibly awkward knowing that I have literally turned it off solely for the sake of whistling. The only thing is, this isn't like to give myself a stage to whistle, it's just because I know if I'm going to whistle, that it's not going to sound particularly good, and it's going to sound a whole heck of a lot worse if I have other music which is in a different key being played underneath, which is not only meaning that what I do is out of key, but it's also meaning that I'm more likely to be out of key just because I'm thinking of the wrong notes because I'm also hearing what's underneath. Do I overthink things? Yes, of course I overthink things. If that's one thing you should have worked out about me by now, is that I completely overthink just about every decision in my entire freaking life. There's an incredible video, which one of my friends sent some, actually didn't send, played for us the other day, which is someone discussing his position as like as a world champion whistler or something like that. And partway through, completely unprompted, this guy just turns to the camera and says, and of course I can't kiss more than 48 hours before a performance because my lips need to be in top physical condition. It's just like no one is... I get kind of the point that's being made. Like, you know, there is actually some... There is, like, at least a somewhat vague physical attribute associated with it. And, like, you can't just do nothing. But just, like, out of nowhere, you can't kiss more than 48 hours before performance. It was just like, good to know? I don't know how I'm meant to respond to that fact. But it was very funny. And so every day when I'm whistling, now I will, if I'm just whistling and one of my friends notices, I will very likely be have someone point out to me that I evidently haven't been kissing enough recently because my whistling is too world class. Or just I'm being annoying and they want to call me out, which is very honourable and I very much respect it. Let's just aim for mech only, or just miss everything. I guess that also. That isn't not mech only. Didn't get the extra one. It won't be a problem, I don't think. Technically, could be there is an edge case in which I'm fighting that, or in which that mech hits me right as the Stromling is about to do the 3 damage attack. I was on 4 health, I think, so that could have killed me, but hey, it didn't happen, so all is well in the world. But yeah, so I was whistling Cantina Band earlier today, because one of my friends started whistling. It was really funny, one of my friends started whistling. But it was like each verse, well, after the first verse, one friend swapped over to the other, and it just went down like a, probably a major third or something like that. And so when it came around to mine, I just popped it down by a minor third. Or it wasn't like explicitly going around, but I was good at joining for the next one, so I just kept moving it down. I don't, because it was just like, well, if the first one went down, let's keep the pattern, and it kind of sounded alright. But yeah, Cantina Band's a fun one to whistle, even though I kind of botched it there. Yeah. If anyone's wondering where the next section is, that's because I don't know that section off the top of my head. And, oh, actually, I guess I could play it in my earphones, because I do now have noise suppression. So I could play it in my earphones and work it out. Because this is how I normally... So I don't want to play this just because, like, copyrighted music, etc. But, I normally, whatever I'm doing, like, if I'm playing LU on my own, I will always be whistling, like, consistently. Which is the reason why I started there, because it's just naturally what I do. I completely realised that, yeah, of course, as long as I'm wearing audio things, I can always whistle along. As long as my earphones don't, like, leak audio, you know what I mean. There we are. but I have no idea how to whistle. Okay. Okay, this is the point where it slowly descends into chaos as it no longer becomes even a semblance of enjoyable to listen to me whistling. Because I don't know the piece well enough. But yeah, like, unironically, 90% of me. I guess it's something I've never really delved into much on the channel, but yeah, 90% of me playing is whistling along, and this is not a fun piece to whistle along to, the Battle of Nimbus Station backing music. I love the music of LEGO Universe, and I very much do enjoy Brian Tyler's work, but this is not the sort of piece to which I would enjoy listening to, enjoy whistling along to on its own. So if you actually noticed, there was a point where I was standing over by the collapsed faction building over on that side, just doing absolutely nothing, and that's because I was going in and going into my sounds and just muting LEGO Universe. Yeah, I mean, 90% of I'm just looking at my stuff like 99. Well, 99, maybe. 99 Luftballons, it sounds like. Oops. Okay, we're more or less clear. There's still a couple on the other side, but bum 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 bum. Wow, that was incredibly close. No, I'm dead. I'm dead. Didn't process. Ah, well. Yeah, so maybe... I don't know. I can't tell if this is audible. Okay, so no, this is being covered up by the fact that I'm wearing earphones. That's cool. I mean, I should probably... If I'm ever going to whistle along to stuff or to play, should probably be pieces I know better. I know, I'm in the mood for another run. Why am I doing another run? I know I was like, I'm down for doing something, but I realised that was a bad decision, but... As I just tab out to Chrome, just to... Let's see if we die before the end of American Pie. And as I watched him on the stage, my hands... Singing with voices already dead. Ain't a great idea if you want to sound good. Fortunately, I don't really care that much. Otherwise, I wouldn't have been whistling for the past 10 minutes. Wow, how did none of those hit? There you are, and that's a fairly good approximation to my internal monologue whenever I'm playing LU. Not specifically American Pie, but just whatever song I happen to have listened to earlier that day. Okay, it really wants me to listen to Freebird next, because it's given me that twice. I'm not going to give it what it wants, but... that was not what I planned. Nor was that. It does just kind of go on like this for absolutely ages. There's a violin or something, which is good vibes. Sounds like a violin. They evidently just like, yeah, we've got this motif. Let's just use it for all it's worth. Well, the rare death to a admiral. And with that, it is 10 o'clock. I am planning on getting to bed somewhat early tonight. I've also found an incredible life hack, which is if I leave my window open and where when inadequate thickness thing whilst I sleep, I wake up really nice and early in the morning. Which is good vibes. No idea if this is necessarily a good idea, but it works. And it got me up at, bear in mind I normally wake up, because it's uni, I normally wake up like sometime between 9 and 10. I woke up at 7 o'clock this morning, which again, compared to me in the past, isn't huge. Compared to me now is gigantic. Still Layla. And that particular series of notes, the bum ba ba da bum, just reminds me so much of Crackling Rosie. It's different, you know. I should just honestly just complete this mission quickly. This just keeps going. It's really the like that's such a small proportion of the song. It's still like a minute left. Not actually quite a minute, but honestly, the thing I've spent the most time listening to recently is just Celeste. Oh, I've got an interesting idea. So we discovered the other day, this is like a really, really niche, obscure, and arguably pointless thing, but I did discover the other day that the sharks do have physical hitboxes. I don't know, but I think there's a chance the sharks... Because I haven't actually been watching the animation, but I think there's a chance that a shark may jump up and eat this. And if it does, then it will have a hitbox as it does so, I would expect. And if it does, that would be hilarious. If I could manage to jump on it, so I'm going to give that a go. There's no way I'll manage to get past the water death plane. So it's like not practically useful. Honestly, there are better ways out of bounds if you really need an out of bounds than any of this anyway. So takes a pinch of salt, but let's give this a go. Okay, so it will feed them. They just get... Okay, they eat it and then get smashed somehow. It's apparently right at the end of Celeste. It's interesting that cloud didn't disappear until I exited. Yeah. So, thank you very much for watching. It was incredibly weird because they just started whistling. I don't know. I think it's a lot easier to do one of these things, yeah, if I have someone to talk to, so I should just send a message to someone. It's just a lot easier to, like, maintain coherence. I'm not known for my coherence to begin with, but, you know. Anyway, yeah, thank you very much for watching. Been BoNS. It's the Celeste theme playing in the background as I leave out. I mean, you guys can't hear it, but it's in my head. Sorry, this has been so weird. I just need to do something for the exam. Thank you very much for watching. I've been BoNS. I'll see you around. Goodbye.